Okay, last track. All right. So here we go. It says a moving particle encounters an external electric field, all right, that decreases its kinetic energy from 933 electron volts to 5,780 electron volts. Okay. So it's losing its kinetic, so therefore it's gaining potential. First of all, what's an electron volt? That is the way we measure energy, especially when we're using particle physics, because it's just much more convenient. Because now we're going to figure out what is an electron volt. I think we've done that before, but maybe not. So this is a good time to do the electron volt calculation. I think it's probably in the slides or something. So this is a good time to look to examine the electron volt calculation, and it's really not bad. It's exactly what it says it is. So how many joules is this? How many joules is that? So, well, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. How do we get that? Well, we take E, which we know is plus or minus 1.6 times 10 to the negative 19 coulombs, which depends on whether it's a proton or an electron. All right, so you got plus or minus E times 1 volt. So that gives me 1 EV, 1 electron times a volt, or 1 EV. So if I've got 9,330 of these, I'll take 9,330 electron volts times 1.6 times 10 to the negative 19 joules per electron volt, which is the conversion. Those cancel. And so that's how you convert that to joules. So I've got 9,330 times 1.6 second e to the negative 19. See, and this is why we use electron volts. See that number? That's a funky number. 1.49 times 10 to the negative 15 joules. It's much easier to work with this. Or it's even in particle physics, they'd say, oh, this is 9.33 kilo electron volts. And if it's an electron going through that potential, you go, oh, well, then the number of electrons, or the voltage then is 9,330 volts. If it's an electron or proton. Oh, okay. So there's that. There's that energy, and then you can compute this energy. And so this is the voltage that they're actually going through, and we can determine the charge on it. Now we've already determined that since this is slowing down as it's going from lower to higher potential, it's not a negative charge, it's a positive charge, because it's going to eventually stop, right? Because it doesn't want to go this way. Okay, all right, and so this is going for, so that'd be the change in voltage then for this problem. So what problem is this? 10. So this is for problem 10. Then the change in voltage that I have is it's going from positive 32, which is V2, minus negative 64, which is V1, which gives me positive 96 volts. Okay. And so the change in electric potential energy is equal to the negative change in kinetic energy, and so I just subtract those two energies up there that I got, and then you can figure out the other one. Was it 5,760 EV? You can figure out how many joules that is. You can do that one. And it's going from here to here, so that's negative, but we make it a negative, so we make it positive. And so you find the change in the energy, which will be a positive change in the electric potential, because it's like it's rolling uphill. It's like an object literally rolling uphill. Right? And then is equal to Q, which is what you're after, times the change in voltage. So you got everything you need. Let's look at the next one. This is an obnoxious one. 2-point charges. So what is the electric potential midway between them? Oh, this is cool. This is a nice comfort physics problem. And this reinforces, so this is problem 13. This is a nice problem to reinforce. We know before, 13. So here's what we have. Q1 is equal to 3.9 times 10 to the negative 6 coulombs. Q2 is equal to negative 7.7 times 10 to the negative 6 coulombs. And the distance between them is equal to 3.5 meters. Now, what if they were both the same charge? What if they were? What if this one was negative 3.9 microcoulombs? What would it be halfway between them? That'd be 0. Got that right. But let's take a look at what we got here. So the distance between, now, what you can do, again, put Q1 here, and then it's got a potential out here. Q1 has a potential out here of d over 2. And so V1 is equal to Q1 K times Q1 over divided by d over 2. Okay, that's its potential. Keep the sign of the charge. And so that's V1. V2 at that point will be K times Q2 over D2 divided by D over 2. Okay, well that's fine. So this is out here, and this, see, this is a big positive, a little less positive, a little less positive, and then this is a, and then since this is a bigger charge, big negative, bigger negative, a little bit less negative. Now I bet you when it gets here, it dominates this positive. Okay, and so you just take the sum of the voltages. You just add them up. You just add V1 and V2. That's it. Once you calculate it, nothing to it. Last but not least, and I am done. I am cooked. Stick a fork in me. I'm done. All right, let's take a look at this next one. All right. Value of Q is 3.8. Okay, so the value of negative Q would be negative 3.8. Just do what I just showed you. D is 5.1. So just add up all the potentials here. Just pretend you just do it one at a time. Do it for this charge. Write the number down. Do it for this charge. Write the number down. Do it for this charge. Write the number down. Do it for this charge. Write the number down. Just like we did on problem 13. Add them all up. And that's what you got for being right here. So this guy is 2 times away. He's only got half. I mean, if you think about it, these two have double the potential right there. This takes away 1. I mean, you could do it by 7 if you're an expert at this. This is a double negative 2 volts, whatever. But this is 1 volt. So now we're just down to like negative 1 charge. And then this one's twice as far away, so it's only half the voltage of this one. So we're adding another positive half to, so it's negative half the charge. See, I already did it in my head using symmetry. But you all can crank it out by hand. All right. But that's the way I'd do it if I was taking like an MCAT or something like that. All right. Which I would never do because I'm not smart enough to do that. Out here, I can't wait to see you all in person. See you on Tuesday, a week from